So welcome you all in the today's lecture of digital signal processing. So in the last lecture we have talked about DFT and FFT, right? And we saw that how can we use FFT to compute the DFT in a fast manner, right? So in a DFT basically we have a less number of multiplication and addition, and in time domain DFT is equivalent to circular convolution. Also we saw the relation between linear convolution and circular convolution. Today we will tell a short trick also to compute the circular convolution. For example, let's take an example. So let's say that xn is 1, 2, 3 and 4, and another discrete signal is somewhere is -3, let's take 1 and 4. So essentially the idea here is that you want to convolve it, right? So I want y of n, that is the convolution, circular convolution rather. So this is a circular convolution with the hn. So what you do basically, you can do it graphically also, right? So you draw 1, 2, 3 and 4. So this index is very important, right? It could be a dash sign below the number, or it is an arrow sign. So these arrow sign will represent the index, right? So this is at index 0th index, right? So this is n equals to 0. So if the arrow is here, so this will be index 0. If arrow is here, so this will be index 0 and this will be index -1 and -2 and so on, right? So this index is very important to compute the circular convolution. Now I'll tell you the short trick that easily you can calculate the circular convolution. So to do that, first of all you have to make both the signal dimension equal. So this is the dimension is 1 cross 4, so I can make it 1 cross 4. So how can I make it? So I simply add 0, so that dimension will become 0. Now what we can do, suppose we want to find the circular convolution of xn and hn. What you do, one signal you shift it in a matrix, and one signal you keep as it is. So you can take any of the signal. So let's say that if a second signal I am keeping here -3, 1, 4 and 0. And what you do with the first signal, just keep those numbers here. So 1, 2, 3 and 4, and then you shift it. Okay, so what will happen? 1, 2, 3 and 4 will come here. Similarly you write it 1, 2, 3 and 4. This will be 1, 2, 3 and 4, right? So this is how you shift one matrix in this form and the second vector as it is. Now you do the just inner product. So 1 is multiplied by 3 -3, 4 is multiplied by 1, 3 is multiplied by 4 and 2 is multiplied by 0. So what you will get if you add all those numbers, you will get 13. So next row you can do the same thing. So you will get 13, 11, -3 and 1. So this will be the answer. So directly you can write the answer of circular convolution. So this is a short trick. So if you want to verify the answer, so directly you can find the result. Now I'll take one more example in which index is changed. So let's say that xn is 1, 2, 3, 4 and 5, and let's take hn also. So hn is 2, let's take 4 -3 and this is 1. So dimension here is 5, here the dimension is 4. And one more thing you have to observe, the index. So I am keeping arrow, let's say here, so that means this denotes n equals to 0 is here. And the second is, let's say I keep it here. Okay, yeah, this is 0th index, this is the -1th index, right? So before doing the circular convolution of these two numbers, so since you have to find the 5-point DFT, right, because next number is 5. So to do that, first of all you have to make both the vectors starting from n equals to 0. If it is not there, you have to make it. So how will you make it? Just shift it. So 3 is the first one, so I'll write it as 3 first place, then 4 and 5. Now the first two I can bring it here, because anyhow I have to circularly basically shift the these vectors in the matrix form, which I told you the short trick. So I can write it in this form, so that n equals to 0 should come here, and similarly hn also I can do the same thing. So right, so before doing that I have to make the size equal, so I will append 0, so that size is becoming equal. Then I will make it this also at 0 position, so 4 will come first, then -3, 1, 0 and 2. So this is very important to because both the vectors should have at n equals to 0 when the sizes are equal. So first you have to make the size equal, and then you bring n equals to 0 index same for both positions. Then you can simply find it out in the same way. So what will you do that? Simply you have to start 3, 4, 5, 1, 2, then shift it downwards. So 3, 4, 5, this is how much? 1, and this is 2, 1, 2, 3, 4, 5, 5, 1, 2, 3, 4, and this is 4, 5, 1, 2 and 3. Similarly you can write the another vector, that is 4, -3, 1, 0 and 2. So you can just find it out. So something you will get like 15, 19, 13, and this was a similar questions was given in the quiz too, right? So this is how you can directly find the answer in a very small time. So continuing the discussion, so we will take now a new topic, that is how can we use DFT for spectral analysis basically, right? So the idea here is why we are interested in using DFT for spectral analysis. So the goal is that you have the real-time signal, right? So your real-time signal could be a speech signal, or it could be a biomedical signal, or it could be a radar signal, right? So that you want to estimate the frequency at what carrier it is modulated, and what is the spectral content in that. For example, the audio is ranged in some band, right? So we are interested in the spectral content of that, so that we can design filters and do some kind of processing. So we want to use the DFT for the spectrum analysis. So but what are the challenges? The challenges is you are having a very short signal or a finite signal, right? So in the real time you have radar signal, so that is very, very short. So radar is kind of very small pulse, right? Or a signal could be long, right, but your spectral content is changing in time. For example, you are recording a music, right? So spectral content will change for the music, because music is played at different pitches, right? So the spectrum content will significantly change over a time. So the time in which the spectrum content remains constant or stationary, that is very short in this case also, when the signal is even long, right? So in real time we have to always work with finite number of samples, right? But what is the problem? When we are using finite number of samples, we will get it will get less resolution and less accuracy. So this is the challenge if we use finite number of samples in a real time. So when we have finite samples, we are basically computing the DFT. So we know that we already knew from the last few lectures that ultimately we want to get the continuous time Fourier transform for the continuous time signal, right? Because anyhow when the sensor is recording, that signal is a continuous or analog signal, and your sampling process does it or makes it discrete, right? So we are interested in DTFT. So this CTFT is also for infinite time duration, DTFT is also infinite time duration. So but we don't have that many samples, right? So we are interested to find it out, the DTFT or of infinite time duration signal in theory, but in practical we don't have a long signal. So what we do, we just find the DTFT for a short time, right? This is also not possible practically to compute, as I already told, because we cannot compute DFT because of infinite summations, so convergence will not happen. So we go for DFT. So we know that when we go from DTFT from infinite time to finite time, then there is something called spectral leakage, right? So that will occur. So that thing we will see in detail also. So let's take an example of a radar signal where radar pulse train is given by PT, which is a very short pulse, right? So this is a very short pulse, and this pulse is repeated. So this pulse is basically periodic. So since it is periodic, we can write down the Fourier series for this signal, and this signal is basically this is periodic with PRI, that is pulse repetition interval, right? So and the frequency of this is basically 1 upon PRI. So when we write the Fourier series expansion for the PT, so that can be written as Cn times e to the power j 2 pi fc minus fpt, where Cn is the Fourier series coefficients, and this is basically your Fourier series kernel, right, which is at fc, and this is shifted by fp, which is nothing but fp is your inverse of PRI, right? So what essentially happens in the spectrum domain, right? Since PT, we assume that it is a kind of infinite signals because it's periodic signal, but in real time we are basically interested to find the spectrum estimation for this one pulse, right? But let's assume that we have a full long signal, and we can write down the spectrum of that is nothing but DTFT of infinite duration signal. So when we find it out, we can simply see that this is exponential. So in the frequency domain, you will get a shifted version of at every FP, right? So this is modulated at a carrier frequency, and this other lobes are basically shifted at every FP, right? So this is the DTFT of infinite duration signal. But what we have in real time, we have only finite number of samples, right? So when we compute the DFT, because we can compute in real time DFT, not DTFT, right? So DFT is nothing but DFT just showing the just samples of DTFT, right? So we can write down that DTFT of finite duration signal looks like, right? And DFT is nothing but just samples. You draw the samples out of it. So we can write down the DTFT of finite duration signal looks like this, right? But original signal was this. So when you compare this with this, you see that these pulses are very low or a small width, right? So these are impulses. But what is happening here? This is kind of spreaded, right? So every pulse is spreaded, right? So you can see that this pulse is getting spreaded here. So the main lobe, this is a main lobe, right? This is shifted here. So every pulse is kind of mixing with each other, and it is kind of spreading down, right? So there is some kind of leakage. This is also known as spectral leakage, because spectrum of each frequency component is kind of leaking into another spectral components. So what is happening mathematically? So we can think of like this, that we have an infinite duration signal y of n, but in the real time we can only process a finite duration. So what we are essentially doing, this is nothing but we have a long duration signal, and we are just feeding finite number of samples at a time. So this can be thought of in mathematics as you are just doing truncating basically yn with some windowing function, right? So this WR is a windowing function, and you can think of that you are just choosing a rectangular window function. So rectangular window function means basically essentially we are choosing some n number of samples, right? So we can write down xn as yn multiplied by WR of n. So this we saw that when we go from infinite to finite, basically leakage is happening. So we'll derive that how the leakage is happening mathematically, right? So to do that, we know that we are using a rectangular window function, so that has this kind of shape, and this is going from 0 to n when we take only the right half. So So when we compute the time domain of this this is in time domain, right? So in the frequency domain, this will be a sinc function, right? So we can say that your x of theta, which is nothing but the dtft of the finite signal, right? This is nothing but dtft of your finite signal. So this can be written as the circular convolution of the infinite duration dtft, and this is window, because what we are doing in time domain, we are just multiplying. So in the spectral domain, it will be circularly convoluted, right? So we are just convolving the y of theta and wr of theta. That is a circular convolution. So we can write it down as the convolution formula, right? So here it should be theta minus del lambda, but it does not matter because dtft is periodic, right? So essentially you can write theta minus lambda or lambda minus theta. That will not affect. Now when we write down the dtft of this, we know that it is a kind of sinc function, right? But it is not exactly sinc function. So in time domain, we are having this rectangle, right, or a pulse. So we can write down the dtft of this pulse is nothing but 1 times e to the power j theta n, where this expansion can be written as in the geometric form. So we get this form. So this geometric form we can convert into Euler's form, where we take this e to the power j theta n by 2 outside, and then internal thing will be simply sine of theta n by 2 upon sine of theta by 2. So we have this factor, right? This factor multiplied by this factor. So this looks like sinc function, but it is not exactly the sinc function. So there is a famous mathematician, that is Dirichlet. So we are replacing it by the same Dirichlet function, and I am following the slides of again my Mark follower. So please bear with that. So the Dirichlet kernel basically, which we have written as this sinc function, kind of sinc function. So when we draw this sinc function for n equals to 11 samples, right? So what will happen? You see that we are getting this kind of curve. So when we increase the number of samples, so this is nothing but we are choosing some finite samples out of infinite duration signal. So when we append more and more samples in our signal of interest or a signal of process, so what will happen? This thing will essentially, main law will be essentially going down, right? So when we go from infinite to the 41 to infinite, what will happen? We get only impulse, right? So that's what I just shown it here. So here, right? So we get only impulse when n is infinite. So now what is happening when n is increasing? Basically you have one main lobe and we have some side lobes, right? So here you see that that the other side lobes are also interfering, and when we are increasing n, the side lobes are all getting lower and lower. So it should be 0 when n is going to infinity. So yeah, so this is one way to avoid these side lobes and the main lobe smearing. So this is one way that you increase number of samples, and there is another way that you choose some kind of window function which can provide you better or less spectral leakage, right? So yeah. So let's say that y of theta is your infinite duration signal, and let's take one example that your infinite duration signal is also looks like a rectangular pulse in a frequency domain, right? So in time domain, it is a kind of sinc function, right? So it is a kind of sinc function. So you can think of your y of n. Sorry, this is y of n. Your y of n is a sinc function in the time domain. So dtft, you get some kind of repeated pulses. So when we write down we have to find the circular convolution of this and w of theta, right? This is also dtft of window that we have already convolved in the last slide. This is the one, right? So when we find the circular convolution with this, so we have to shift the second signal for circular convolution. So when we shift it for different lambda, right? So lambda is going from minus pi to plus pi, right? Because it is periodic. DTFT is periodic between minus pi to plus pi or 0 to 2 pi. So when we shift it and we keep it this position, what is happening, the resultant spectrum will looks like this, right? So what is happening for a different shifting, when we add it the final lobe, what will happen, we get this kind of curve. So when you see this curve, basically your main lobe is also getting, we are interested to get this curve, but what we are getting is this one, right? So we are showing just for a single band. So you can see that your main lobe is also kind of, there is a dip here because of this, right? Because side lobes are also mixing with the main lobe, so this will bring it down. So instead of this, you are just getting a dip here. So this is causing you the main lobe smearing, right? And there is a sharp transition here, but due to this windowing or due to choosing finite number of samples, getting a smoothing curve, right? And we get this side lobe leakage also. This side lobe leakage we will also study in detail in coming slide with different examples. So yeah, so essentially you can think of with another example that what is the effect of this window, right? So let's take in time domain two exponential signal with different amplitudes A1 and A2, where A1 is much higher than A2, and theta1 and theta2 are the different frequencies. So when we compute the TTFT of this, we get the impulses at theta1 and theta2, and these are repeated over minus pi to plus pi. So when we draw this in the TTFT spectrum, basically interested in minus pi to plus pi, where we get these two pulses, and these other two pulses are basically repeated, right? So let me erase this because this is, yeah, okay. So yeah, so this is the basically the DTFT of your window. So this I already told that we get this kind of almost sinc function, right? So when we just we have to convolve it, right? So this is the convolution. So we have shifted it. Now we have to multiply these two operations. So when we just convolve these two y and w, we get what actually? So this is nothing but the delta, right? So when we multiply delta, so that function will also be shifted at that particular position, right? So the deltas are at particular alpha. So when we convolve with that any function, that function will be shifted at that alpha, right? So what will happen, these what we call this sinc will go at these impulses. So you can see that this blue curve is showing you the impulses shifted at these higher peaks, right? So this is shown here also. So what we did actually, A as it is, right? A1 is as it is, and your W1 is shifted at theta1, right? Because there was a delta here, so W1 is shifted at delta. So what was W? W was this sinc function, which is shifted at theta1. So every higher peaks which is shown in blue color is due to this peak, right? And this sinc function, this W function basically is also going into these small pulses, right? So that is shown in red color, right? So this is the second part. So where you can see that the main lobe of another signal due to this another frequency content. So these are nothing but the two frequency contents, right? So when we are finding the spectrum of any given signal, we are interested to find it out the two distinct frequency components. But here, since the A1 is much higher than A2, the frequency content of the second signal is kind of smearing or hiding behind the side lobes of first signal, right? So you can see that this red curve is mixed with the side lobes of first signal, right? So in this case, basically we are not able to find the another frequency component, although there were two frequency components in the original signal. So this is called as side lobe leakage or side lobe interference. So this we can study with another example, so in which we take two complex sinusoids, and they are very closely spaced in frequency, but this time we are taking almost with same amplitude. So when we convolve these two functions, what will happen, the resultant function will look like this, right? So when we shift those DTFT of your window at theta 1 and theta 2, so theta 1 will be your blue color curve, and when you shift it at theta 2, this shows you the next curve. So when you see here, since they are very closely spaced, the resultant function, which is the DTFT of your finite duration signal, looks like this, right? So what is happening, your main lobe is smearing actually, so you cannot distinguish. There are two frequency components, but from this main lobe we can say that there is one frequency component, right? So this is the intuition by choosing when we choose a very limited finite number of samples in the practical scenario. So what will happen, your DTFT sometimes has the main lobe smearing as well as side lobe leakage, right? So these two are very important points when we analyze finite duration signals in a practical case. So this thing we have already studied the same thing. So we'll see that when we have a continuous time signal, we just pass it through ADC, which gives you the XM, that is a discrete version of that, right? And this is the kind of DFT processing. So when we find the CTFT, theoretically this looks like this, and DTFT for infinite case is looking like this, but there might be aliasing because this signal is not band limited, right? So definitely you will get aliasing. So this is due to the sampling process. So if you do the faster sampling, you can avoid this aliasing. So now we find that theoretically the truncated DTFT, these three distinct frequency components are kind of smearing into each other, right? So from here you cannot draw any information of three frequency components, and DFT is nothing but the sampling of those DTFT. So you are basically drawing some samples from the DTFT of the truncated version, right? So here you can get some kind of grid error, right? So when you append zeros, basically you can remove that grid error, right? So this is we have already talked about. So this is aliasing error, smearing error, and grid error. Now we will see this thing in with another example in which we take a decaying exponential. So xt is e to the power minus bt ut. So although these kind of signals are not important in practical case, but for studying the relationship between CTFT, DTFT, and DFT, we are taking this kind of signal. So let's choose the decaying rate as 2000 pi and sampling rate at 30 kilohertz. So when we choose only 8 number of samples which are looking like this, so this is a kind of decaying curve, right? So when we feed these 8 number of samples inside this block, right now we are not appending any zero, so you can think of we are feeding the 8 samples in computing the DFT, and this you can basically simulate in MATLAB as well. So when we do simulate it in the MATLAB, basically you can define the sample frequency time, that is nothing but the 1 upon fs, and this time step you can define it basically, and this is your generated signal, that is e to the power minus pt of n, right? So that you can write it down. So now we compute the ff of x, and then we shift it so that you get the positive half of the spectrum, and then we can basically plot it for every frequency point. So this command basically providing you the frequency spacing between the. So I'll explain this thing in like this. So let's say that you draw the spectrum. So this is a frequency points, right? So for some frequency point you get particular frequency, right? That when you want to convert in hertz, you have to find it out that how many frequency coefficients are corresponding to 1 hertz. So essentially you have to compute the delta of f, where delta of f is nothing but sampling frequency by the number of FFT points. So since we are sampling at a 30 megahertz and we are suppose sampling, we are just doing it by 8 sample DFT, right? So we have to divide this frequency plot by 8, right? So that denotes a 1 hertz actually. So this is how we can compute the or basically you can basically divide the whole frequency spectrum, and then you can obviously plot it. So when we plot it, basically it looks like this. So I'll just draw the plot. So this is the DFT plot, and you get the positive half as well as negative half, right? So this is the DFT. So when we compute the CTFT here, so here we are interested in CTFT of the analog signal, and DFT we got this kind of shape, right? So we have to relate basically CTFT, DTFT and DFT. So to do that, basically we compute theoretically CTFT of the analog signal, DTFT of infinite duration discrete signal, finite duration discrete signal, and then practically DFT. So to do that, we are taking again the same example, and since we cannot compute practically, so we try to compute the previous decaying exponential CTFT by writing this thing where the B was actually 2000 pi, right? So we can write in this form basically, and CTFT, we know theoretically the CTFT of this time domain, the time domain, this is nothing but the analog signal. So the CTFT of this is given by B plus j omega, right, where omega is 2 pi f. So when you can write the MATLAB code to plot the CTFT, right? So B is from, as I told, B value is 2000 pi, and f I'm ranging it from minus 2 lakhs to 2 lakhs. So spacing is 100, so that the curve looks good, right? Because there are too many points, so I can take a spacing of 100. And then this is the CTFT, which is the same expression, that is 1 upon j2 pi f plus b, right? So then you can plot it. So the CTFT looks like this for this decaying exponential. So we can similarly draw the DTFT also, right? So when we compute the DTFT of ADC outputs, so we know that DTFT after sampling is denoted by x of n, and that is nothing but a t sample at every nt, right? So just you replace the decaying exponential, the time t, by nt, right? So you get essentially this kind of signal, right? So this e to the power minus bt is can be replaced by or by a to the power n un, where a is less than 1. Why? Because this is a decaying exponential, so we know that a is less than 1. So this kind of signal we have already seen, and we have already know that we already know the DTFT of this, right? So DTFT of this is nothing but 1 upon 1 minus a to the power minus j omega. So please remember the DFT. So that is for infinite duration signal. So when we plot this using MATLAB, so simply you can define the omega, capital omega, from minus 3 pi to plus 3 pi, right? Because DTFT is periodic and we are interested in the band minus pi to pi, but we can also draw the two replicas, although we can draw many replicas, but for the visualization purpose we can draw two replicas along with the main spectrum. So DTFT in MATLAB can be written as 1 upon 1 minus, the same expression is coming here in MATLAB code, and then you can plot it basically, right? So when we plot it, and we are interested to plot DTFT onto the CTFT, right? So that we can realize actually what is happening in the case of DTFT from CTFT, right? So you see that when we are plotting, we are multiplying by t, right? Why we are multiplying by t? Because you know already the CTFT to DTFT conversion sampling theorem. So you know that how x of omega can be related with capital, sorry, let me write small omega. So capital small of omega is related with the analog frequency x of omega, right? So these are notational difference. So although this is the DTFT, right? So when we plot it, basically, or we are again I will show that. So we are just plotting with respect to not omega, we are plotting with respect to omega divided by pi, right? Because DTFT is from minus pi to plus pi, right? So when we normalize it by, you get a normalized frequency that is from -1 to +1, and that is a normalized radian per sample. Similarly, for plotting CTFT also we are normalizing it by Fs by 2. So Fs by 2 is your folding frequency, so that is also normalized between -1 to +1. So when we plot it, basically you get this kind of signal. Your CTFT is a red curve and DTFT is a periodic version, right? DTFT is always periodic, so DTFT is in blue color. So here you can see that due to sampling we get aliasing, because the original signal was not a band limited signal, so we get aliasing in the case of DTFT. So this is the expression for converting your the CTFT to DTFT, where DTFT x of omega is kind of replicated at every 2 pi, right? And this t is there, so we want to plot both the signals simultaneously, so the t is going here, so that we can plot both the signals on a single plot. Now we have drawn this signal, and we got till here, right? So we got the spectrum of infinite duration signal, but in the real case or a practical case we can only talk about n number of samples, finite n number of samples. So what will happen, we have to draw the DTFT of truncated signal. So that is also not possible in a practical case in a computer. Why? Because in computer we can only compute the DFT, not the DTFT. So but we can draw it, we can write the DTFT theoretically. So what is that? So x of n, that is nothing but the finite duration signal, that can be written as x of n multiplied by some window. So we are choosing some finite samples out of infinite samples. So DFT for a finite sample can be given by this, which is theoretically, right? So this is the convolution in frequency domain, right? So this is the truncated DTFT. Okay, so or when you compute it basically by hand, you can write in this form also, which is nothing but the geometric form. So that is 1 upon a e to the power j omega to the power n upon 1 minus a e to the power minus j omega. Now when you plot it using MATLAB again, so I am just plotting all three by normalizing it, right? So you can see that DT of infinite duration signal, which is shown in a blue curve, and this is the finite time DTFT. So you can see that there is some kind of right in the red curve, there is some kind of smearing. So the main lobe is also smeared. Also you can see some kind of side lobes. Okay, so your truncation by a window can cause some kind of spectral leakage in the DTFT. Now although we can improve it, so here so even if we append more and more zero, it will not improve this smearing, right? Because when you append more and more zero, your DFT will your DFT will just draw more samples, so it will not reduce this leakage error, right? So zero padding don't change any leakage error, that you have to keep in mind, right? How can you improve it? If you take more and more, draw more and more samples, so your leakage will go down, obviously. Now in the real time we can compute DFT, right? So the DFT expression we know already. This is the DFT expression. So essentially DFT, what it does, just draws the point from truncated DFT. So it is just drawing the points. So when you appoint zeros, so it will draw more points in between, so that grid error can be reduced, but smearing will still remain as it is. Now if you summarize all the results in a single slide, so you can see that your CTFT is looking like this, which is actually physical signal. It could be a speech signal, logic signal, or it could be a radar signal. So your infinite duration DTFT can cause aliasing, although it can be removed by faster sampling. So DFT is causing your leakage error, and your DFT is causing the grid error, right? So we'll close my lecture here, and we'll continue this discussion in the next lecture.